Hello everyone and welcome on today's video. My name is Wouter Pere, I'm the founder and main developer of GHEtool Cloud, and today we're going to talk about a new feature within the Optimise for hybrid systems methods within GHEtool, which is about balanced bore fields. So just as a recap, we talked a couple of months ago about hybrid systems in the 3-part series. Now, if you have not watched that series, it's linked in the video description below, and it can really help you understand why this method we're going to talk to you about today is different from the other ones and why it can be helpful for your product as well. So, hybrid systems are a general term for every HVAC system which has a combination of multiple technologies. So for our geothermal hybrid system, it's a ground source heat pump in combination with, for example, an air source heat pump, solar thermal collectors, dry coolers, waste heat, etc. And the main advantage, we said earlier, of hybrid systems was that it's good for investment cost and system reliability. So because you have multiple technologies, you can use the benefits of all of them and you can spread and optimize your investment. And because you're relying on multiple technologies, if one of them fails, you still have another technology as a backup. So it's a reliable system. Now we then also talked about the concept of geothermal potential, and we had the geothermal potential for power, we had geothermal potential for energy, and we had bore fields with no geothermal potential at all. And then we discussed about two methods which were already implemented into GHEtool, which was Optimise for power. So there our idea was we want to get the maximum amount of power out of our bore field at every instance. So in every month of the simulation period, we want to be able to have this amount of power available. And then we also had the methodology to optimize for energy. And there the idea was, well, we want to extract as much energy from the ground, or we want to exchange as much energy with the ground, and therefore we are willing to install a little bit more of our power for a ground source heat pump, for example, in order to get most energy out of the ground. Now, the difference between those two methods, it's linked in the video description below. Please go ahead and watch that if this is not clear to you. So what we then had for both optimization methods, if we optimized for power, we got the profile above, where we saw that we are both limited by the maximum and the minimum average fluid temperature. So this bore field we set had no potential for power, but there was still some potential for energy exchange, because as you can see, due to the imbalance, the fact that the ground cools down year after year, there is potential for extra cooling in this later years of the simulation period. And we can easily extract a little bit more heat from the ground during this first month. So there is potential for more energy exchange. Now what we then said, well, if we optimize for energy, we have this temperature profile where we see that we reach the limits in every month of the simulation period. So here we said that this bore field had no geothermal potential left. So that was the main distinction between both of them. But as you can see, both of them also have an imbalance. So year after year, the ground cools down, and here also, year after year, the ground cools down. So a question we received quite a lot is, well, what afterwards? So if you optimize for 20 years, what's in the 21st year? And what will your system do then? And also looking at it from a really sustainable perspective, namely, even if you optimize for 40 years, what after that period? So we received quite a lot of questions about balancing this ground. And that's why we created this week for you a new optimization method, namely Optimise for balance. Now what the idea there is that we want to keep the ground temperature constant over the years. So in comparison to the Optimise for power and the Optimise for energy, we now want our ground temperature to stay the same until infinity, let's say. And the main advantage of this method is that we have the most robust design, the most reliable design, because we know that the efficiency of our heat pump, the temperature of our ground will be the same through every year. So there is no problem when it comes down to our simulation periods. There is no discussion whether it's 20 years or 40 years, because it will be the same. The main disadvantage, however, is that there is quite a lot of geothermal potential left. Because we're not going to both temperature limits, we leave a lot of geothermal potential for power and for energy untouched, which is again here a trade-off, and we will see when we go to GHEtool Cloud later in this video how this turns out. So for the methodology itself, we chose an adaptation of the Optimise for Power methodology. So there we had the objective that we want to maximize the power that we can inject in during cooling or extract from during heating the ground at all times. But now we have an extra condition, namely that we want to keep the ground balanced. And this is typically a profile you will see when you optimize for balance, is that you will reach one limit and then the ground will stay balanced. So it's actually the Optimise for Power which that slight difference. And this is the optimization algorithm. So what we do again, as was the case with the Optimise for Power, is we start with an hourly simple simulated building. So we have hourly data. We calculate the load duration curve and we start with a fixed bore field size. Then we apply this load to a bore field, we calculate the hourly temperature profile, and we're going to check a couple of things. So first of all, we check if we cross the minimum average fluid temperature threshold, and if we do so, we're going to limit our peak power in heating. If we cross the maximum average fluid temperature limit, then we're going to limit our peak power in cooling. So that was the case when we optimized for power. Now we add another criteria, namely that we do not want more than a certain amount of imbalance. So what we do is we say to the optimization, well, we want at max 5% of imbalance, let's say, and then we're going to check even if the temperatures are below the threshold or within the thresholds, but if there is imbalance, we're also going to correct for that. So let's say that the minimum average fluid temperature is above the minimum threshold, so we do not cross this limit, but we see that there is an imbalance which cools down the ground year after year. We're going to limit our peak power in heating in order to make sure that we keep our ground in balance. When we do that, we end up with a check. So if the minimum and maximum fluid temperatures are within the limits and we have less than a certain amount of imbalance, we're going to say that the bore field is optimized for balance. And if it's not, then we're going to iterate, and we do this until we are both within the limits and also we have no imbalance left. So this is the theory. Let us now go ahead and look into GHEtool Cloud, how you can use this method for your own project. So here we are in GHEtool Cloud. I opened again our project from last time when we talked about Optimise for Power and Optimise for Energy, so that we can now show you what's the difference when we optimize for balance. So just as a recap, we talked last time about difference, how you can use these methods for your own project, and we said, well, we're going to optimize the power for a bore field of 10 by 9, then for a bore field of 9 by 9, 9 by 8, and then we also switched to the Optimise for Energy methodology, and then we came to the conclusion that we want 250 kilowatts in heating, and we end up with this result. So now what we're going to do is let's go back to this 9 by 9, and you can see we indeed reach the minimum and maximum temperature limit as we would expect with this method. And we saw that we installed 224 kilowatts in heating and that it had 73% of our heating demand on average. But as you can see, the ground cools down. There is a rather big imbalance of almost 170 megawatt hours per year in extraction. So let's go ahead and duplicate this scenario, and let's call it Optimise for balance, and I will call it 5%. So let's go ahead and save this. And over in our general tab, you can see that we have created another button here, Optimize for maximum balance. And here you can say what the acceptable amount of imbalances you want to tolerate. So perhaps you say, well, we want the whole system in balance, or you say, well, we can live with 10 or 20% of imbalance. By default, it's 5. You can go lower, but the problem is that if you, for example, go to 1%, that it can take quite a long time to optimize it, and depending on your specific load profile, perhaps there is no solution. Because we work, or the methodology is based on a load duration curve, and if you have a very, very high amount of full load hours, perhaps we cannot go to that 1% of imbalance. So that's why I suggest sticking at 5%. The other options with regard to the limit of the geothermal power, etc., are all in place. But let's go ahead and calculate it for the Optimize for balance and compare this to our solution to Optimize for power. So here we are again, and as you can see, now we optimized it and our bore field is rather stable. And you see that when we compare it to the imbalance of 170 megawatts, that we are now at only 10 megawatt hours. So it's not exactly balanced, but it's way more in balance. And here you can see the results in yearly heating and cooling demand. So we have 150 kilowatts in cooling and 170 in heating, whereas the Optimize for power, we have way more power in heating. And also our percentage dropped from 73% to only 41%. So this is a really conservative way of optimizing everything, because we want to have that balance. So what you also can see, and I want to draw the attention on, because we talked about the imbalance, etc., but you see here that we have 267 megawatt hours of geothermal heating and only 193 megawatt hours of cooling. Now, the important thing to know is that this is talking about cooling and heating demands. So it's building loads. There is still a heat pump and an SCOP and an SCR in between in order to calculate the geothermal load internally, leading in the end to this geothermal imbalance. So this was for 5% imbalance. Perhaps this is a little bit too conservative. So let's go ahead, duplicate the scenario again. And let's say that we are willing to accept 25%. So we go to the general tab and we now say, well, let's go for 25% and calculate it again. So this is the result we end up with. And as you can see, we have now 67 megawatt hours of imbalance. Our ground cools down a little bit more. And we also have a little bit more, or quite a lot more, I should say, heating demand. So this is how you can play with it. And the last thing I wanted to show you is that this solution actually converges towards the solution for Optimize for power. Because if you say, well, I allow for 100% of the imbalance, what you then say is that, well, it does not matter what the imbalance is, and it will optimize with disregard of what the percentage is basically, and you end up with just optimizing for the power. So as you can see, we have optimized this for balance. We have still the same cooling down year after year. And we also have the same solution as before, but now with another method. So in the limits, it goes to the Optimise for power, but perhaps if you say, well, I want a little bit less imbalance, you can use this method to really optimize, also keeping that imbalance in mind. So I hope you find this video interesting. We really hope that this third option to optimize your imbalance can be helpful for your project as well. If it is, please consider subscribing, leave a like, share it with your colleagues, and I hope I can see you again in the next video. Take care.